Welcome back, everybody. After a long delay, I just looked back, it was like 8 months ago, I started a series on solar power, and I thought I would dive back into that. This will be the third time I've tried to get back into this, and so we'll give it a go this time and see if I like how this turns out. The last time, the audio, I just didn't like the way the audio turned out, so I scrapped it. So we're going to try this again. And if you're watching for the first time and you're wondering why I've got a blue thumb, you can go check the link in the description on how I did this. It's a table saw accident that was completely preventable, but just in case you're wondering what this blue thumb's about, that's what happened. Anyway, back into the solar series. If you haven't watched the first one, it was about 4 months ago, link in the description below. Watch that one first, and then we'll kind of dive in to the rest of this based on what we found on that one. First of all, before we jump into sizing the batteries to that 7.9 kilowatt hours per day, let's talk about the different kinds of batteries we can be using. There's a whole variety of batteries out there, but I'm going to pretty much focus on lead acid style batteries for a couple reasons. One, the lithium technology that's out there looks really promising. Right now the cost is pretty high on it, and I hate to say it's unproven. It's unproven in home usage. It's very well proven in power tools and cars and such things. But as far as home usage, it's really not caught on real great yet. I think in the future we will see that. And it's really not caught on the commercial side, like remote power situations, mainly because lithium has one huge drawback to it, and that's charging when it's below 32 degrees. Most lithium-based batteries, you cannot charge them when it's below 32 degrees. Like tool batteries, like a DeWalt battery, for instance. They have a sensor either built into the charger or the battery, and when it's below 32 degrees, you cannot charge that battery. It will destroy the battery. So that's one big drawback to lithium. If you're using them on like a remote power site, yeah, you got to keep them, above freezing for them to work. The other kind of a drawback is they don't do real well when they get real warm either. If you get them real warm, they can have a runaway power situation and pretty much have a meltdown. That's not to say that's very common occurrence, but it can happen. So in most situations, I don't think we would ever see that high enough temperature to actually have that, but it's something to think about. There's other technologies out there, and let me grab my list and we'll go through them real quick. Okay, I got my list here, and the reason I'm using this list is some of these I just don't deal with very often, and I'm sure I'm still going to forget some of these even with a list. But we're going to start with the deep cycle lead acid batteries. These are the most common in use. They are tried and true. We know what they're going to perform like, what their limitations are. These are what most people are using on solar applications off-grid, is some type of lead acid deep cycle battery. You also have lead acid shallow cycle batteries, which are pretty much what's in cars for starting. A lot of amperage real quick, but they don't really like to be a long-term power draw on them, a constant current draw. So they're made for quick, lots of current, and then they're pretty much, that's what they're there for. Deep cycle batteries are they're really not designed for a huge current draw, outrush current draw, but they're designed for a longer term steady draw on them. And so those are the two most common lead acid batteries. We'll dive into the specific different kinds of lead acid here in a moment. But of course you've got the nickel iron, nickel cad, nickel based batteries. Really popular in power tools for quite a while. Lithium's kind of taken that over. But the nickel iron, I know some people have had really good luck with iron-based batteries on off-grid systems, but I'm not super familiar with them, so I'm not even going to dive into it. Of course, you've got sodium-based batteries, and there's several of the different kinds of those out there. Again, not going to dive into it. We've already talked about lithium batteries, and then there's what's called a flow battery. The flow batteries set up, again, not familiar with them, but I know it's a technology that's out there. Certain people really promote it. Not going to dive into it. We're going to focus pretty much on lead acid batteries here. So if you're really interested in lithium batteries, this is probably not the place to look. But you know, I'm kind of hoping to see some growth into that, and hopefully the price will come down in the near future on those lithium style batteries, and we can try them out and see how they work. So now that we've got all the different kinds of batteries out of the way, and I'm sure I missed a couple in there, let's kind of look at the difference quickly between lithium and lead acid batteries. I'm not going to spend a lot of time on this. This is a subject you could debate to death on which one's better and all the virtues of both. But just quickly, let's look at a few things that we can compare these two batteries. One might be energy density levels of the batteries. In other words, for the weight of the battery, how much energy do you get out of that battery? We can also look at net efficiency of the batteries. And then there's other subjects with batteries like toxicity, the ability to recycle them, and so on and so forth. So let's look at the lead acid batteries first. The pros on these batteries is they're relatively cheap. They're a tried and true technology. We know what we're going to get out of those batteries, and we know their limitations. They've been around for a long time, so we know how to deal with those. Now the energy density, in other words, how much energy do you get out of that battery for the weight of the battery and the size of the battery? Yeah, they're not real great. They're pretty big, bulky, and for the size of them, you know, you only get a certain amount of capacity to that battery. So the other things to look at are energy efficiency of the battery. In other words, for the power you put into the battery, how much were you able to get out? In general, lead acid batteries are about 80 to 85% efficient. So you lose about 20% right off the top. So you lose 20% of the power from your solar panels or wind right off the top going to the batteries. That's just the way lead acid batteries are. So the last thing we'll look at with lead acid batteries is toxicity and the ability to recycle them. So obviously lead acid batteries, you have the ability to recycle them very easily. You can take them down, you can get a few bucks out of them. They're easy to recycle. We know how to do it. It's not a problem to recycle lead acid batteries. And of course, they're somewhat toxic. You've got acid in them. Pretty easy to deal with just common baking soda. You can neutralize the acid. So, you know, they're something that we can handle easily. We know how to deal with them. So it's not a huge deal. Obviously, you don't want to go dumping the acid out into the ground and all that kind of stuff. I've seen that done before. It's not a good idea. It's better to take it to a recycling center and dispose of it properly. And most of that lead that's in those gets reused again. Almost all of it can be reused. So I encourage you to recycle those batteries. Now, lithium batteries are more of an up-and-coming technology. We're making great strides. I'm really surprised how far they've come in just the last few years. And I think in the near future, we may see them, the cost come down and be more available to homeowners, off-grid systems and such. Right now, the cost is still pretty high for, let's say, kilowatt hour you get out of those. But they are a very efficient battery. The energy density is much better on a lithium battery compared to a lead acid battery. For the weight and size, you get a lot more energy out of that battery than you will a lead acid battery. So that's a huge plus for the lithium batteries. Now, as far as being able to recycle these, they are recyclable. They're a little harder to get recycled because most recycling centers are not set up to handle them, especially if you live in rural areas. You're going to have a little bit harder time finding something to do with used batteries. Now, down the road, that may change, and they may be just as common as a lead acid battery by the time these lifespans on these are done. So since we're talking about lifespans of batteries, let's kind of look at the difference between lead acid and lithium batteries. Lithium looks like it has potential to have a longer lifespan than lead acid batteries. lead acid batteries in general, if you treat them decent and never draw them below an 80% depth of discharge, you got to leave that 20% on the bottom. If you get down into that last 20% of the battery, you're really shortening the lifespan of that battery, big time. So if you can keep that above that level and keep that charge up above that 20% and never go below 80% depth of discharge, which we'll cover in a minute, you can expect to get between 8 and maybe 10 years out of the typical lead acid battery. Now, I know there's other batteries out there that will last longer, and the flooded batteries tend to last a little longer than sealed lead acid batteries, which we'll cover here in just a minute. So on average, though, you can expect to change out your batteries about every 10 years. Now, you can run them longer. The efficiency of the battery just starts dropping off. You don't get as much capacity out of the battery. And I know those folks out there, oh, I've ran my batteries 20 years, and that's cool. I'm not disagreeing with you. I'm just saying that on average, 8 to 10 years of what you're going to get out of lead acid batteries. Lithium, on the other hand, since it's a new technology, we really don't have a good track record of how long these would last in a solar setup. So I think that probably the potential is around 15 to 20 years, maybe. Don't quote me on that. But that's possibly another advantage with lithium-based batteries. And that's about as far as I'm going to jump into this lithium versus lead acid debate. I don't want to, like I said, you could spend a lot of time just debating on the different kinds of batteries and which is better and blah, blah, blah. Not what we're here to do. We're just going to discuss a basic system and how to plan for it and how to deal with your battery system. A lot of people do this in the exact opposite order. They'll buy solar panels, batteries, and then figure out what their load is, which is a huge mistake. So now that we're focused on lead acid batteries, let's look at the different kinds of lead acid batteries there are. There's 3 main types that we need to be concerned about. The flooded, which are very common, golf cart style batteries, the big ones that you see in like phone companies use, telecommunication companies use them a lot, these big, huge cells that have a lot of capacity. They're 2 volts apiece, big flooded cells. They used to be really common. They're not as common anymore, but they're still out there. The next one is a gel style battery, a gel cell. And I don't really recommend gel cells. We had a lot of experience using gel cells. We went through this phase of, gel cells, the greatest thing since sliced bread. And what we found out on solar sites, our radio sites, is they're very finicky. And if you either discharge them too much or charge them just a little too much, you've ruined the battery. And the old style solar controllers we had were really prone, if we had lightning nearby, to lose their mind and overcharge the battery. And they didn't need to be overcharged by much. And if you got them discharged too much at all and they got cold, boy, that battery was done. So we had really bad luck with gel cells on remote sites. Now, in a more controlled environment where you're able to watch it, they may be okay. But again, they're a little more finicky than the next style of battery I want to talk about, which is an AGM battery. And here's what AGM stands for. And the reason I'm not saying that is I can't say that first word to save my life without sounding like a complete idiot. So that gas mat, sometimes you just have one of those words that just won't come out of your mouth right. And that's one of them. Anyway, so AGM style batteries, I really like them. I'm not going to go into all the details about how they're built and all that. That would just take way too much time. You can Google it. It's really it's a tried and true technology. It's been around for, I'm guessing 15 years. I'm not sure when they first came out with AGMs, but the telecommunication industry is pretty heavy into AGMs. They're non-spillable, no maintenance, and they've been pretty bulletproof. We've had really, really good luck with them. That's what I use here at home, as an AGM style battery. And there's some drawbacks to them. One of the biggest drawbacks is they say they don't vent, but anytime you're charging a battery at any higher rate, they're going to vent to some degree. Even these gas mat batteries will vent some. The problem is there's no way to get that vented material back into the battery. So over time, if you go through a lot of quick charging cycles, like a high amperage input to the battery, they will vent, and over time that battery will lose capacity because you're losing a little bit of the electrolyte in the battery, unfortunately. We don't run into that very often in our remote sites. We don't have a high enough charging capacity to make them vent much, if at all. So it's never been a big concern. But if you've got several kilowatts worth of solar panels out there and you're charging at a high capacity, that's something you might want to think about. A flooded style might be more up your alley. The reason I like the AGMs is they're maintenance free, and I'm terrible about maintaining batteries, so I love them. If you're really good at taking care of batteries, then a flooded cell is probably more up your alley. So flooded cells might be the best option for you. Just remember, with flooded cells, there's quite a bit of maintenance you have to do to those batteries, especially if you've got a system that's got a fairly high capacity, the ability to charge your battery system. If you've got a big solar array and you're charging at that high capacity, you're going to vent and you're going to have to replace electrolyte quite often. I'm not talking like every day or anything, but you need to be checking those batteries at least once a month during those periods of high charging, because you're going to lose electrolyte, and if you get that below those plates, boy, you're just asking for trouble. So just keep that in mind. Flooded cells, I think, in general, will last a little longer than AGM style batteries just because you're able to replace the electrolyte. But there's a lot more maintenance involved. If you're a person like me who does not like to go mess with batteries, steer clear of the flooded batteries. And I know this question will come up: should I buy used batteries or should I buy new batteries? That's a tough one. If you're just starting out, you don't want a huge investment into it. I know it's so tempting to go out and buy used batteries, forklift batteries, whatever kind of battery, and try and get a lot more use out of those. I've seen guys take old telecom batteries, the big, tall, wet cells that are clear on the sides that you can see the fluid inside of them, that had been in service from maybe a phone company for like 20 years, and they took them out. Somebody's used those and went through and more or less overcharged the battery to try and get some of the sulfide off of the plates. And it did work. There's still some capacity. It's just a reduced capacity. So can you do it? Yes. Do I recommend doing it? Probably not. And here's why. You don't know how those batteries were treated wherever they came from. If you can verify how they treated those batteries, then by all means give it a go if you can get them cheap, because you may be just buying a big problem child that you have to deal with. And so be really careful with used batteries. I know there's this group out there that thinks forklift batteries are the coolest thing ever. And remember, they're just a lead acid battery, a deep cycle lead acid battery. Most of them are either AGM or gel style. So they're just a battery. Before we jump into sizing our batteries for that 7.9 kilowatt hours per day, let's talk a little bit about battery voltage and how it affects the efficiency of your system. It's actually fairly important to decide early on which battery voltage you're going to be using. In general, on inverters, the higher the voltage input to the inverter, the more efficient that inverter is. Also, when you get to higher voltage battery systems, in general, you can use smaller wire sizing to your inverters and between your batteries. And the reason for that is, let's take an example here. These are two important laws that you need to remember. One is the power law. The way I always remembered this when I was starting out, and things have changed a little bit, was penguins visiting Italy, P over VI. And of course, Ohm's law here. You're going to need to know these when, well, you should know them. There's lots of online calculators, so you don't need to memorize these unless you're a geek like me and you just do. So let's take a look at the current on just, say, 1,000 watts of power being used. If we take 1,000 watts and divide that by 12, we wind up with about 83.3 amps. Take that same 1,000 watts and divide it by 48 volts, you get a little over 20 amps. So you can see that you have less current flowing through those wires if you use a higher voltage system. What that means is you don't need to buy big, huge honking wire to go from your batteries to your inverter when you're running a higher wattage inverter, especially once you get over 1,000 watts. You know, I've seen some of these 12-volt inverters claim to be 3,500 watts, even some of them a little bit more than that. Well, you take 3,500 watts, you're talking a lot of amperage there. What is that, off the top of my head, 260 amps? I'll put the answer here. But that's a lot of amperage. So you have to run fairly large wire. And the reason you have to run larger wire is, if we look at Ohm's law, all wire has some resistance to it. And the bigger the wire, the less resistance it has. So at this point, if we take a look at Ohm's law, and we can figure out pretty easily what our voltage drops can be across that piece of wire. And let's use 10 gauge wire. I'm not saying you'd ever use 10 gauge wire between your inverter and your batteries if you've got any kind of sized inverter at all, but just as an example. So a piece of 10 gauge wire that's approximately 10 feet long will have about 0.01 ohms of resistance across that 10 feet. So using what we found out earlier, the 83 amps that we would be drawing at 1,000 watts across 0.01 ohms will give you 0.83 volts of drop across that piece of wire. You can pretty much just round that up to about a volt drop if you figure connectors and everything in. So say your batteries are at 12.6 volts. Your inverter's actually seeing 11.6 volts. If you go much lower, your inverter's going to start giving you alarms. So now let's look at that same scenario using a 48 volt system. At 48 volts, same equation, you're going to have about 0.2 volts of current drop. So same situation, say your batteries are at 48.6 volts, your inverter is going to be seeing 48.4 volts. And again, when you're working with lower voltage systems, those 12 volt systems, it's much more critical to have the correct voltage getting into those inverters. You don't have a large window to work with there. It's not like AC where your voltage can be from, like 120, it's just numbers here, 123 down to say 105 volts, and whatever's hooked to it's going to work fine. With 12 volt systems, you got a pretty narrow window, usually about maybe 14.5, 15 volts down to about 11.2 volts. Most systems will operate. You've got a pretty narrow window to work with 12 volt systems. So the least amount of voltage drop you can get, the better. So when you get into these bigger inverters, you're going to have to run a Mondo sized wire to lessen that current draw. Also, wires rated at whatever amperage. There's charts all over the place. You can look up the size of wire and what they're rated at. Now be very careful with that, what they're rated at thing. A lot of times they're figuring AC current, not DC current. And they don't really care about voltage drop. The AC side of the world, the electricians of the world, they don't care if they lose a few volts across, a span of wire. When you're dealing with DC and especially 12 volts, you're really concerned about any voltage drop. So I recommend, if you're planning on going off-grid, looking seriously at a 48 volt system. I know the inverters are more expensive, but they're more efficient. They're usually more robust, and you'll just be happier. You won't have to buy this huge wire to run between your inverters or between your jumpers on your battery. So just keep that in mind. Something to think about. If you're talking about an off-grid like cabin or something, 12 volts may work fine for you. The batteries are easy to get. So, whatever floats your boat, just keep that in mind. So it looks like it's time to carry this over to another video. Tried to squeeze this all into one video, but I get to talking about this stuff and kind of geek out. And so this is going to be carried over to the next video. And I just realized I took the blue wrapping off of my finger. So on the green screen, I wonder how that shows up. Well, we'll find out in editing, won't we? Anyway, I want to thank you guys for watching, and we'll continue this on to the next video and hopefully wrap the battery stuff up in 2 videos. And sorry this kind of took a little longer than I expected, but these are all points I thought probably needed covered if you're really serious about an off-grid system. So as always, thank you for watching, and we'll see you on the next video.